Hello, and welcome to the International Foundation of Robotics Research panel on field robotics. I'm the moderator, Greg Dudek, and I'm super excited to be hosting this panel with three astoundingly good speakers, Daniela Russ, Roland Siegvort, and Stefan Williams, who I'll introduce in greater length in a moment. Let me make a few prefatory remarks as you get settled into your Zoom rooms and watch this panel unfold. All right, so we'll be talking about field robotics. What is field robotics? It's a branch of robotics dealing with the outdoor and unstructured world. And it's often tightly coupled with service robotics, which is a closely allied area also dealing with unstructured environments. Field robotics very broadly includes three main areas: terrestrial robotics, robotic systems that go into the forest, the desert, or that move on roads; robotic systems that move in and under the water, for example, on the surface or below the surface of rivers and lakes and oceans; or robotic systems that move through the air, that can do surveillance over factories, that can check parks for forest fires, that can do surveys of the Amazon rainforest. Field robotics is arguably the most important branch of our sprawling field. I'm sure there are a few people in other branches that might attempt to make the same claim, but those specious claims notwithstanding, I think there are many reasons why this might be true. Most of the world is still outdoors and unstructured, and most of that outdoor world is volumetric, meaning not just a surface, but a three-dimensional volume. And that means most of, or no, it doesn't mean, but partly as a result of that, most of the outdoor world remains poorly mapped, where modeling and surveillance is very weak compared to what's available indoors. In fact, as I think many people know, the bottom of the ocean, which is the part of the ocean that's best understood, is less well mapped than the surface of Mars. And our happiness as a species, our survival, and in fact, the entire biosphere depends on understanding that natural outdoor world, managing the resources, managing the ecosystem, monitoring what's going on, and perhaps also extracting resources from it. So there's a huge need for robotic systems that can move around in that vast outdoor world. The field robotics as a whole, and moving into robotics into the outdoor world, has a very large set of significant challenges. These include mobility, navigation in the face of exogenous forces like wind and currents. There are flexible structures, there's terrain roughness, there's non-uniform friction. Perception in field robotics context is hard because there is a lack of strong priors or constraints on what is out there, as opposed to in a factory where you can understand and model many of the things in advance. And there's a complex and uncontrolled natural world to deal with. There are variations in lighting, there's non-rigidity, there's diversity, there's tremendous richness, which is tremendous scientifically, but hard in terms of using standard techniques. There are uncontrolled objects and uncontrolled surfaces with great diversity and richness that makes machine learning or classical methods very difficult because of that diversity. And there are huge problems in deployment and logistics that makes field robotics pragmatically challenging. Many countries have tried to address it, building large or national scale research networks, such as the IFRR in Australia, or Canada's NSERC Canadian Robotics Network, or Field Robotics Network, but that still makes the problem hard, or leaves the problem hard. In addition, there's a problem of robustness. If you want to deploy systems in challenging outdoor environments, the systems need to work and work consistently and repeatedly due to the logistics of deploying them. You can't go back and recode every 10 minutes or every hour when you're deploying robots in a manner that's hard to get to. So we have three amazingly good panelists. I mean, these are the best people in field robotics, but these are arguably three of the best robotics in the world. In fact, it's not even arguable, it's clearly true. The first speaker is gonna be Roland Siegvort. He's a professor of autonomous systems at ETH Zurich. As we all know, that's one of the world's leading academic institutions. Incidentally, if I listed all the achievements and accolades of our three speakers, I could easily consume the entire half hour we have for their talks. And so I won't, I'm just gonna touch on it. He was the former Vice President of Research and Corporate Relations at ETH Zurich. Then we'll have Daniela Russ. She's Viterbi Professor of Electrical Engineering and Computer Science and Director of CSAIL at MIT. And then finally, we'll have Stefan B. Williams, Professor of Marine Robotics at the University of Sydney, the head of the School of Aerospace, Mechanical and Mechatronic Engineering, and also part of the Australian Centre for Field Robotics. And by the way, among Stefan's many impressive achievements, he was also born in Canada, and I believe he's still even a Canadian citizen. And so with that, let's move on to hear what Roland has to say to us.
So welcome everybody. It's a great pleasure to give you a couple of inspirations in this field of field robotics. And I'm actually focusing, because we have only 10 minutes, mainly on design and some elements on control and learning. So let me just go ahead. We already heard field robotics is typically in unstructured environment, dynamic environment like forestry, agriculture, search and rescue, construction, and so on. These are environments where you have typically the unexpected, which will happen. It's really highly unstructured. In this field, in research, I think you can not only do theoretical work, you have to go out, you have to do something in the field to learn about the challenges. And first, in field robotics is typically the understanding of the task. You have to really understand fundamentally what is the task, and additionally design the robots for given tasks. So let me start with a couple of examples of robots which have to define for given task, or mainly given motion in typical environment. And let me start with two-wheeled robots, which both of them have been designed actually by students at ETH in their last year of bachelor in the team. So the first is Vertigo, which is a robot which the students ask themselves, can we build a car-like robot? It's about 40 centimeters long, on wheels, with front wheels and steers, but which can also go on walls and ceilings. And they actually came up with this, what I call a hybrid between a flying robot and a wheeled robot, with two propellers which can be pivoted around two axes, each of the propeller. And if then you do a proper control, you can actually go and move towards a wall, and you just adjust the propellers and you continue to move on the wall. Of course, this, if I would have played the sound here, you will see it's about the same sound as a helicopter. It's very loud. But at least this all of a sudden allows us to go to places where you never would have imagined to go with wheels. Additionally, wheels are typically pretty good on flat ground. So we had another project, the Ascento, which actually designed a robot, which I would call is something between wheels and leg robots. So it has actually two wheels. It's balancing on two wheels, but it can adjust both legs with different motors independently. With this, it can also jump. It can jump upstairs. It can go on sidewalks and so on, and has much more flexibility in our daily environment. So the biggest part of our research in the last 20 years was actually about flying robots. And we were at the origin of all this quadrotor and multicopters. And soon after we worked on this, we asked our question, can we actually fly longer? Helicopters are highly inefficient. And so, of course, it was already known that this hybrid or VTOL systems, vertical takeoff and landing system, can do a better job. And again, there was a student team actually starting, and they wanted to build a VTOL system which can carry stuff far, but still can get off the ground like a helicopter. And here you can see actually the result, which then ended in a startup company. And I call this a minimalistic system, which is really optimized for this task. It has two propellers and two flaps. And only with 4 degrees of freedom, you can do the whole movement. And actually, thanks to really sophisticated control, they are even able at pretty high winds to stably land with only two propellers and the flaps. This, like this, you can have probably about 3 or 4 times have longer flight times. We ask ourselves also, can we fly forever? And this was actually inspired by some project with the European Space Agency, which had some ideas to go on Mars. And we said, probably it would be nice to fly on Mars, but you would like probably to fly forever, because landing and get off the ground is very difficult. What we did is then 2018, an airplane, a drone, which is about 3 meters wingspan, which flew 24 hours, and they pushed this further. We have demonstrated in 2015 an 81-hour flight. And this is actually a very interesting device for field experiments. For example, for earth scientists or people which are trying to study the glaciers here in Greenland. So we had an expedition with people from earth science to go far out and get images from the glaciers. They want to see how the glaciers move, how they develop, And today it's extremely difficult. You cannot carry out regular airplanes there. You have a problem with the fuel up there. And with these airplanes, you can fly out hundreds of kilometers, taking images and coming back to the place. Of course, this is not a vertical takeoff and landing because it's optimized on very low weight. And so you need a little bit of landing spot, but it's not huge. So up to now, flying robots are always meant to be as far as possible from obstacles and environments. But imagine if you would have a flying robot which can actually fly towards walls, actually connect to the wall, generate forces against walls. And this is actually rigor, which is our newest design of a robot, which has, in principle, here you can see this rotors. It's a hexacopter, but the propellers, they can be rotated around this central arm. And by doing so, we have all of a sudden much more degrees of freedom than a standard multicopter. And so we can then fly, for example, rotate around the point without moving X, Y, or you can actually, without changing the attitude, moving X, Y, Z, which means that you can generate forces in all directions and independently also move in all directions. And this offers a lot of new capabilities, which is shown now in this next slide. As demonstrator, you can fly with this helicopter with a pen just connected to a helicopter, to a blackboard, and then just generate a force towards the blackboard, and you move lateral to the blackboard. And you can imagine, of course, this is probably not the main applications, but meanwhile, we are using this for a lot of other applications. There is a new startup just started a couple months ago, which is doing, for example, this type of inspections where you go and have a sensor which flies in contact so that you can measure corrosion on a structure or different elements you have to measure in this environment. So I think the next generation of flying platforms or flying robots can replace these people which are hanging on ropes in very dangerous situations. And we have already shown that a lot of these applications can be done by a helicopter which is omnidirectional, which can actually generate forces in all directions, move in all directions with all different attitudes. So with this, I will have a first stop probably for some questions or some discussion with my colleagues on the panel. You probably know this, this quadrant of relevance and rigor. And I think if you want to really push robotics, but this same is for other fields, towards real applications, you have to combine both of them. You have to be on one side rigorous in your modeling, your understanding of the whole system, but you have to also consider the usefulness of what you're doing. And today, typically universities are rather in this part. They are rigorous, but they don't consider so much the use. And on the other side, industrial research and development is more in this quadrant. And I think we have to push more this, because there are the disruptive innovations. There is really new elements which come together. And so you have to go out, and field robotics is a perfect field, because in field robotics, you have to really do a lot of new development, fundamental developments. But on the other side, you have to go also out in the field and understand what is needed. So probably this challenges some of my colleagues on the panel, what they think about this vision, that we should probably also a little bit more also consider the use, and then follow the use, and not just mention, yes, this system could be used in this field, and then at the end we are solving something which is not really the use case.
So I think we have a brief pause here, just in case one of the other panelists wants to interject a question or a comment, and then Roland will continue on. Steph, you have your hand up, but you're muted.
Yeah, Roland, I tend to agree. I think, and in my talk, I'll show some use-inspired basic research challenges in marine robotics and some of the work that we've been doing. But what would you characterize as the most significant challenge that we might address as a community going forward, that sort of might really see us taking this field robotics up into, supporting things in society, given, environmental challenges, pandemics, all kinds of things happening at the moment?
Yeah, I think we have to, as a researcher, really to go out in the field. We have to push the limits, not only showing once that it in principle works, but probably multiple times. Of course, it's not the task of universities to go up to a final product, but we have to do a little bit more. I tend to say sometimes people are solving virtual problems. So they start with a real problem, probably really from the use side, and then they actually cut it down to make it simpler and simpler so that it's nicely solvable, but it has nothing to do anymore with the real problem. And I think as soon as you are moving out to the real environment, you will actually see the challenges. And so you have to do this task. It's not easy because it's already difficult enough to solve the theoretical problem and make progress on this end. But I think you have to team up with the right people to do both so that we can really have more robotics coming out really in real use for a lot of different fields.
Roland, I agree with you. I would interject that in fact it's an interesting balance that that we have the opportunity to strike between inventing new knowledge, between advancing the capabilities and then showing that what we are doing is actually relevant. And so to me, it's important to have both, because by developing the foundations, we have better understanding of, and we can predict better how the systems might work. And then when we take these systems with solid foundations into the field, they end up being more robust, they end up being more understandable. And that is especially important as we begin to think about bringing machine learning into the robots that we field, precisely because there are challenges with explainability, interpretability, generalizability of machine learning techniques.
That's a perfect move over to the last slide. I have only one slide left, which is actually about machine learning and these novel algorithms. And as a mechanical engineer, I think it's wonderful what you can do in some fields, but I think it's also a little bit dangerous that people blindly do everything with learning, black box learning, end-to-end learning, which I don't think that it works. I think learning algorithm will not replace models, but rather enhance model, and enhanced models are required. Imagine if you want to really learn scene understanding, images. I think the only way to do this fast and efficient is if you have rendered images. Otherwise, the annotation is very difficult. Or you want to generate motion primitives with a robot, for example, for getting to walk. You have to have a model so that you can learn at least the first element in simulation, because you cannot learn millions of different movements. And this is probably the same for flying. If you have aerodynamics effects, which are very difficult to model, there I think learning can help, but you have to have a basic model. And I would like to end with a nice example from Marco Hutte's group from ETH about learning to walk. So he has an extremely good model of his quadruped robot. And thanks to this, and he actually learned even the non-linearities. You can do actually a lot of simulation. And what he then did with his team, he learned that the robot can get up from every arbitrary position laying on the ground with the legs in whatever situation. And this was all learned in simulation. You cannot imagine if you want to do this really with a real robot, it will break. But the result is, because the model is very good, that the robot is able to get on the legs from whatever position. And I think this is, for me, a very nice example that we should be careful with new tools, not forget the old tools, which do a wonderful job, but complement them and bring them together so that you can get even better. So with this, thanks very much for your attention, and I'm happy to have then more discussions at the panel.
So Roland, I would love to jump in and continue about learning. So in particular, you've argued that we need models, and at some level I agree, but don't you think the models keep us limited in some sense in the capabilities that we can actually accurately model with physics and mathematics? They keep us in the scope of movement, but when we want to get to reasoning and decision making, this requires symbolic reasoning and abstractions. How do we combine the models with the ability to be in these more symbolic, higher orders of abstraction?
That's a very good question. But I'm pretty convinced that today's tool will not allow us to come on this level. And I would also say that we as humans, we have a lot of models which we don't explicitly understand, but we have models. And these models, of course, part can be learned, but if you want to learn from scratch, it's extremely difficult. And by the way, it's interestingly also animals, most animals, they are born and can immediately walk. So they don't learn it. So they have obviously already something through their genes. And I think we have to bring really this in a very wise and good way together. Otherwise, we will fail on pure learning end to end. We will not able to learn ourselves. For example, if you do a design of a robot, you have to understand. And understanding for me, it's somewhat model. So you can probably all of a sudden have a wonderful new device which has been evolved and learned. But if you don't understand why this solution is the best solution, it's very difficult to learn for a next design.
I think that's great. Let's switch to Daniela and we'll go through all the speakers, then we can have an open discussion at the end. So as you know, our next speaker is Daniela.
Well, hello, everyone. Let me see if I can make this work. Okay, so can you see my screen? I hope you see the right screen. I have a bunch of windows open. So I'd like to continue with what Roland discussed and what Greg said at the beginning by telling you a little bit about what motivates me for going after field robotics applications. Although I would say that I am equally interested in the science of autonomy and intelligence and the engineering, which takes us to fielded applications. And so I believe that over the next year and over the next decade, humanity will have some major challenges to contend with. For instance, winning the war on COVID-19, dealing with climate change, curing disease, ending inequality, ensuring sustainability, eliminating poverty. It would be easy to think about this list and feel disheartened, but I personally don't. In fact, I feel quite hopeful because when I look around at how we live our lives today, when I talk with all of you, our colleagues in robotics, I see the many ways in which technology in general and robotics in particular has helped to make the world better. Just try to imagine a day in your lives without the World Wide Web, the smartphone, GPS, and what they enable. It is important to also imagine the doors that our work will open in the future. And so this doesn't mean that we are all set and we have no more challenges. We have a lot of challenges to invent new sciences, technologies, and solutions. And I believe that that science and engineering are blended together. And in fact, in our work, we are advancing both the science of autonomy and the engineering of autonomy. And I would like to share with you two ways in which robotics is helping to make the world better, one for the short term and one for the longer term. For the short term is the fight against COVID-19, and for the longer term, it's the fight to preserve and rescue our climate. So let me tell you how our science and engineering of robotics can be effective against COVID-19. And I would say that we've all seen powerful images of frontline healthcare workers that show up and care for their patients, even at a risk to their own health. And we can never say thank you enough to express our gratitude, but what we can do is to give them better tools, to give them more intelligent tools, to give them more powerful tools. And the tools that we can immediately develop and deploy today are rooted into many years that our community has helped develop. And so I want to start by summarizing a few ways in which our work in field robotics in particular has been used recently by multiple countries to help address the pandemic challenge. And so 16 countries around the world have used robotic technology for public safety, for non-clinical public health, for public works. 7 countries have been using for clinical care. We've also have uses in maintaining critical infrastructure and in doing field operations to ensure quality of life. We've had many deployments to help with supply chain automation and to provide non-hospital care. Now, in many ways, the robots that have been deployed are either manipulator robots or ground robots. And I'd like to tell you about a robot that we developed at MIT over the past month or so. And this work is rooted in our prior work in mobility. And in particular, this work is rooted in our prior work to develop autonomous vehicles that can be deployed and that can work side by side with the people who exist in the cars. So here what you see in this video is an autonomous car developed at MIT. This car used a machine learning approach to learn from drivers how to drive. And the machine learning engine is coupled with correct execution with model predictive control for execution. And in combining machine learning for the high-level symbolic actions of the vehicle with a model-based controller that ensures the execution is correct, we are able to push the boundaries of what a robot like this is able to do. So this robot has never seen this environment. This robot was trained in an urban setting, in places with buildings and sidewalks. And when we took the robot to the woods, we were able to take advantage of the symbolic learning in order to get the robot to operate without any further training. So the robot just worked. Now, part of this training uses a simulation engine, and this simulation engine allows our robotic policy to fail multiple times in simulation using realistic images, and so it's really cool to be able to have one data set that could be modified in a multitude of ways, in an infinity of ways, if you like, in order to figure out how what is the best, most optimal policy. Okay, so how do we go from this field deployment to fighting the pandemics? Well, this is what we have done at MIT, and in fact, we have used the navigation and coverage support that we have developed in the context of other applications, and we have created a UV disinfecting robot. You can see in this image. This robot operates indoors, but its capabilities are very much rooted in work that has been done in a different context. And you can see this robot. It's disinfecting all the the food supplies and the air in a 4,000 square foot facility, which is the Greater Boston Food Bank. It takes about a half an hour to do the disinfection. And this is tremendously valuable right now because, many communities who have been very impacted by COVID-19 in the Boston area actually use this food bank as a main supplier for their food items. Now, before I go to climate change, I want to show you one more robot that we have done during March. And this robot we developed in order to help address the ventilator supply shortage. I'm sure you have heard the news reports about the ventilator shortages facing hospitals. And this problem is even worse as we consider the world at large. Afghanistan, for instance, has only 400 ventilators for a population of more than 36 million people. So it's urgent to come up with an affordable option that uses easily accessible parts. So what you see in this video is a solution we developed at MIT and open sourced for the world to use. The solution was also implemented by 2 companies in the United States. And this robot consists of 2 hands, the gray pellets in the image, with this robotic hand, we're able to convert an ambubag, which is a manual ventilator that is inexpensive and readily available, into an automatic ventilator. The solution uses simple components like cards, windshield wipers, batteries, sensors, metal plates, and some electronics. And so these are 2 examples of how we can take our work developed with other objectives with longer time horizons and make it relevant and usable today for problems that require the whole humanity to step in to help. Now, I'm gonna move to my next topic and tell you that we are also thinking about another huge societal problem, which is how can robotics help with climate change? And specifically, my interest in climate change is rooted in some recent research from the Intergovernmental Panel on Climate Change that has characterized a warming of 1 degree Celsius above pre-industrial levels due to human activity. And the estimate is that this number will go up by 1.5 degrees Celsius somewhere between 2030, which is 10 years from now, and 2052 if human activity-induced warming continues at the current rates. Now, our planet is a feedback system, and we in robotics understand feedback systems. And so, in my opinion, the objective of keeping warming to less than 1.5 degrees Celsius should worry us. Because we cannot continue to go in one direction. In fact, we have to figure out how to cool the planet by 1 degree Celsius. And this is where we can begin to ask how to employ a wide variety of robot systems to help us understand climate change, to slow the impact of warming. And we can do monitoring and modeling of the environment. We can do interventions to preserve biodiversity, to manage food supplies, and more. And so, inspired by these ideas, we've developed a suite of technologies that help us monitor and understand coral reefs. And since coral reefs are like the canaries of the environment, studying them is important. And so I want to show you 2 aspects of this work. One is a new robotic tool we call Sophie, the soft robot fish. This robot has a soft tail that is actuated by pumping water in the blue channels you see in the picture. And the robot also has dive planes that enable the robot to control its position in the vertical column. The controls, the electronics fit in the orange head, which is hard. The tail of the robot is soft. And so with these components, we can control the robot to move forward, to go up and down in the water column, and to turn. We can also get the robot to move extraordinarily fast. In fact, in about 100 milliseconds, this robot is able to change the swimming direction. And this is because of the flexibility we have with a soft robotic actuation system. And 100 milliseconds is on par with what real fish can do. And so, so this is a new instrument. We would like to introduce this instrument in coral reefs to observe the reefs and to also observe the marine life without disturbing it. And that means not making noise and not moving the water in ways that are unexpected for the fish. So here's actually me next to the robot, next to Sophie. And this is a video that shows you more about how this robot can move in the water column and what kind of feedback it can get. So you can see this robot is able to glide past coral reefs. You can see that the little fish and equally the big fish are not disturbed by the robot. The robot swims by undulating its tail, and it can control its own buoyancy so that it can operate at multiple depths. The robot takes feedback from the world through a fisheye lens, and so what it sees is complex images like what you have seen in the video. And so here you can take a closer look at what's inside the robot. The robot is fabricated using rapid prototyping, and the design is fairly easy to fabricate. It's really quite exciting to have this kind of autonomous intelligent tool that can be deployed to monitor how the coral reefs are doing, to take data about the coral reefs without actually disturbing the life in the reef. Now, if you look at these pictures that capture the robot, you see that they look very green and blue, and that's not what a normal coral reef looks like. In fact, if you dive, your eyes adjust, and you see a very different picture. In fact, you see pictures that look more like this. You see pictures that capture Nemo in its true glorious colors, and you see pictures like this. So what is the problem? The problem is that when you take images in water, color gets distorted because water absorbs the various color wavelengths. And so here what you see is, in fact, what happens with ambient light. You see that at 1 meter, 2 meter, 3 meter, 4 meter, 5 meters, if you take pictures of a colored palette, all those colors look more or less blue and green. If you introduce white strobe light, by 5 meters, you're still in the realm of dark colors. And so we have a solution we call adaptive illumination that is able to enable robot fish or any other underwater device to capture images in true color. And here's how the instrument operates. You can, if you can measure the distance to the object we are trying to image, we can compute how much light of each color gets absorbed. And then using a multicolor strobe or multicolor illumination device, we can control the synthesis of the inverse of the effect of water into the scene so that the images get taken as though there was no water in between the camera and the object. And in fact, doing this allows us to capture images in true color. And here you can see 3 instances of field deployments of this instrument. And you see the images taken with regular technology at the top and our technology at the bottom. I have pulled out patches from the image so that you can see the difference in color between the regular technology and the adaptive illumination technology. So it's very exciting to be able to study the coral reefs with autonomous robots, but also autonomous robots that are able to capture some of the critical elements like color. So in closing, I would like to observe that if you think about where we were as a society 20 years ago, we had a society where computation was with us, but computation was a task reserved for experts because computers were large and expensive, and you needed to have expertise in order to know what to do with. And so over time, we have made progress, and now computing is so prevalent, we don't even notice how we depend on it anymore. And this raises an interesting challenge. What can we do with robots? How can we create more intelligent, more powerful robotic devices, robotic tools that will continue to help us understand the planet and address some of the grand challenges that are ahead of us? And with this, I'm going to stop sharing and happy to answer questions.
That was tremendous. Let me suggest we let Stefan talk, and then we'll take questions in the context of the panel for all 3 of you at the end.
Okay.
So Stefan Williams.
Yeah. Thanks, Greg. So today I'm going to, I guess, continue on in the same vein as Roland and Daniela. I'm going to focus on some of the work that I do in deploying autonomous robotic systems, particularly in a marine context. I'm a professor of marine robotics at the Australian Centre for Field Robotics here in Sydney at the University of Sydney. It's fairly early in the morning for me today, but really excited to be part of this panel. So over many years, we've focused here at the ACFR in our marine program on developing platforms and sensors that are suitable for deployment in underwater environments. We've done a lot of work on navigation and mapping, planning and control, data analytics. So a lot of the fundamental sciences that go underpin sort of our engineering of these systems. I'm going to talk a bit more similar to Roland's discussion about sort of the use case driven work that we do in terms of working with a broad range of colleagues around the world to help understand oceans and some of the impacts of changing climate. So I think it follows on quite nicely from Daniela's introduction as well. Over the past couple of decades, we've worked all around the world with a variety of different colleagues, not only in developing the engineering sciences, and a lot of my PhD students have focused on that, but on supporting studies in ecology, archaeology, and geoscience, and trying to understand how the information that we can collect with robotic systems in a field context can support some of these studies. So we've worked all around Australia in supporting better understanding of impacts of changing climate. We've worked in Japan on similar kinds of problems, but also helping to document deep sea hydrothermal vent sites, as well as doing some surveys offshore Fukushima following the tsunami there. In the Mediterranean, we've done a lot of work in archaeological sites, and I'll talk briefly about one of those, and a bit of work in North America and the Caribbean. So we've really had some opportunities to be involved in global studies, trying to understand what's happening in our oceans using a variety of different platforms. So we deploy autonomous underwater vehicles and ROVs. We've had instruments that have been deployed with other people's equipment. Here in Australia, a lot of our support has come through something called the Integrated Marine Observing System. This is an Australian federally funded program, part of a national collaborative research infrastructure scheme. So physicists get synchrotrons and astronomers get telescopes. The marine community came together about 13 years ago and really hashed out a set of infrastructure that would help Australia understand its marine estate. And Australia relies very heavily on the marine environment. They've so far invested nearly $200 million in infrastructure to support the sciences in the marine environment. And this program has been extended for another decade. IMOS really focuses on a whole variety of instruments, including moorings, robotic floats, instrumented animals, all kinds of things. And we run an autonomous underwater vehicle facility associated with this program. So as part of that, we've made a commitment to long-term monitoring of sensitive reef habitats around the country. And this includes tropical reefs in the north and more temperate reefs in the south. So Australia kind of straddles the divide between those tropical coral reefs and temperate kelp-dominated environments. We're also starting to think about venturing further south into polar regions as well. But as you can see from this slide, we've been very busy going back on an annual basis to help scientists understand the changes that are being wrought in our sensitive marine habitats. So here's an example in Western Australia where we were surveying some reefs during a significant warming period. We caught the reefs just before a significant bleaching event, and we've been going back on an annual basis looking at changes. And that's helping ecologists understand not only sort of the mortality that comes from those bleaching events, but also how the reefs are recovering. And there's been some widely reported bleaching along the Great Barrier Reef over the last few years. The robots are collecting not only imagery, but also 3D structural information. So we're able to look at how these reefs are changing, not only visually, but also the structure, which has impacts for you know, the life and fish and things like that that live within the reefs. Another impact of climate change has been increasing cyclone activity, and Lizard Island, which is in the north of the Great Barrier Reef, was directly hit by a cyclone in 2014. We were meant to be on the island when the cyclone hit, so we were not able to proceed with a bit of field work as planned, but managed to get out there a week after the cyclone. So immediately following significant impact from a tropical cyclone, we went out and we surveyed sites around this lovely tropical island, fantastic place to do field work. And we well, in addition to using robotic systems, we also used diver-held imaging systems. And we came up with this technique that allows us to very rapidly survey these reef environments. So we put a pole in the center of our survey area, wrap a rope around it, and basically swim around in circles. And this allows us to collect these, what we call reef records, which are a few thousand images. We can stitch these together to build detailed models of the environment. So this is one example of one of these reef patches, about 100 square meters of coral reef. We can reconstruct the very detailed 3D structure and associated texture maps on top of these records. This allows us to get not only the imagery, but also the 3D structural complexity. In the middle of this particular chart, you can see we've been back. We started out with 6 monthly intervals. We're now on a regime of annual surveys. And what we can do is register these surveys through time. And we thought we'd have this great story of recovery from cyclones. Now, unfortunately, Lizard Island was hit by a second cyclone in 2015. So you can see here after the first cyclone, pretty healthy looking coral reef. Second cyclone, this particular site was hit, was affected pretty severely. And then in 2016, we had extensive bleaching along the extent of the Great Barrier Reef. So the remaining coral sort of died out. Here's another example, 14, 15, still looking pretty healthy. This one was not affected by the second cyclone, and extensive bleaching in 16. Another example, and in this case, there seems to have been some recovery in 2017. Last year, we went back to these reefs, and what we can see here is one of these patches where we've seen very severe bleaching impact. But in November last year, my team was up there, and you can see evidence of significant recovery. So there's lots of coral recruits that are growing in these environments. So it's really helping ecologists understand the dynamics in these reefs, which I think is something very exciting to be part of. Another study that came out a couple of years in Nature Climate Change was taking data that we'd collected along the New South Wales and Tasmanian coasts. There's significant warming in these parts of Australia being induced by changes in the East Australian current, which is bringing more warm water into southern latitudes. Here they took imagery that we collected, identified key species of invertebrates, and looked at their distribution along the East Australian coast. Then they took climate change models that were predicting out to the 2060s, under various scenarios, commensurate with the IPCC predictions, to estimate range shifts in some of these key species. So, and all the modeling suggests that there will be a poleward migration of these sensitive organisms. So we'll see more tropicalization. We've seen huge impacts in the northeast of Tasmania induced by urchins. I think approximately 15% of the Tasmanian coastline has been converted from kelp-dominated forests to urchin barrens. So we're already seeing significant impacts from these changes in oceanographic conditions. Now, our robots are able to collect huge amounts of data, tens of thousands of images. So we do a lot of work on helping our colleagues manage this data. We've got big online archives that provide access not only to the imagery, but also to the annotations that are being provided. So we've got hundreds of thousands of annotations on this imagery. We've done a lot of work on both unsupervised and supervised techniques for, machine learning to help scientists process a lot of this data. One example, one of my current PhD students has been working on looking for lobsters. So lobsters is a key species of the fisheries in Australia. So we're taking AUV data, the navigation data, the imagery. We've trained a convolutional neural net to identify lobsters. We can then project those detections onto 3D models in the environment that the vehicle is surveyed. You can see these are quite complex imagery. They're identifying lobsters quite reliably with a relatively small number of examples, based on some of the latest developments in these vision techniques. We can then start to correlate lobster presence with rugosity, or the structural complexity of the environment, to help both our ecologist colleagues and fisheries managers to better understand distributions of these key species. Now we have to be a little bit careful because lobsters also look like, in this case, these are little finger sponges. So, making sure that we're getting good data out of these classifiers is important. Finally, in terms of sort of some of the fundamentals, we've been thinking about how to do broad scale mapping of the environment, combining imagery with underlying bathymetry. So the structure of the seafloor gives us an indication of what we're likely to see in different reefs. This is a paper that one of my PhD students presented at the recent IFRR. So here we're learning relationships between bathymetric structure and the imagery that we collect with the AUVs. We're making probabilistic predictions of where we can find, key species like kelp. There's extensive screw shell rubble, which is being induced by introduced species in Tasmania. And we're thinking about how to characterize the uncertainty in these models, which will allow us to then better select the location where we deploy our vehicles to collect informative information for these models. Now, one of the big significant challenges that people talk about in the marine robotics context is making sure that number of deployments equals number of recoveries. So, we spend a lot of time throwing vehicles into the water. We want to make sure that we're getting them back. And we work in very different conditions. These are on the left and right here are examples from the Bass Strait, which is the stretch of water between the Australian mainland and Tasmania. Sometimes it's glassy and mill pond-like, and other times we have very significant weather, which we have to contend with. Understanding how to safely deploy these sorts of vehicles is a bit of a challenge. Here's an example where we got the vehicle caught up in a lobster pot. The ship ended up side on to the swell. We bounced the robot off the side of the ship a couple of times, and had some pretty extensive damage. We managed to get some bits of plastic and other things together, straighten things out, and we're back in the water sort of the following day. We've done work in doing some very exciting work in Greece, looking at archaeological sites. This is a place called Antikythera. It's a small island between Crete and the Greek mainland. There's a very famous wreck there, which yielded this Antikythera mechanism. It's a device that was used by the Greeks to predict phases of the moon, and using technologies that people didn't understand or didn't realize existed in ancient Greece. until the discovery of this wreck. We were asked to survey this site. So we took our robots, one of our vehicles to Greece, made a model of that environment. Archaeologists used those models to map. So we took the maps that we produced. They were able to identify some artifacts within the models and then recover artifacts related to this wreck. This is a lead anchor stock. We then were asked to return the following year because they realized there was further evidence of these wrecks and potentially a second wreck site. So we were able to do that. But one of the challenges here was that we were using prior maps to plan our vehicle deployments. Our first dive of the first campaign, we put the vehicle down. We knew there was a cliff sort of at the edge of the bench where the wreck was located. We planned a dive. The vehicle went out, started tracking across at about 50 meters depth, and then all of a sudden dove down to 70 meters, turned around and started coming back up, then stopped. We tried to abort it. It ended up sort of stuck on the base of this cliff. We thought, this doesn't look particularly good. And so we had an ROV, which we deployed. And this is some footage sped up here showing our AUV, right at the base of the cliff where we expected it to be. And if you look carefully, you can see a fishing line caught over top of the robot. And so here was an example of us using, now this is not autonomous, but this is me being a little bit glad I played a bit of Xbox with my son, getting in here to, find the robot, figure out how we could recover it. We decided in the end to grasp the vehicle just above this antenna, to drive the ROV down, bringing the vehicle with us, and we were able to do a safe recovery. We then continued on with the rest of the campaign, managed to develop those maps I showed earlier. So really being resourceful in the field is quite necessary in a lot of these sorts of cases. Now, there's a variety of examples of vehicles that weren't quite so lucky, that have been lost at sea. And this is, I think, one of the big risks of this kind of work, whether it's in deep water induced by pressures, really pushing the envelope and putting vehicles under ice and having things, not return. We had one very close call. This is a day when I arranged to fly back to Sydney. We had one more day of surveys. I got a call once I was back in Sydney saying, the robot's on the bottom. It's not coming up. We've run out of fuel. We're going to have to leave the site. By the time they got back, the vehicle had come off the bottom, disappeared. We talked to our colleagues in the marine rescue and in CSRO who were giving us different ideas about where the vehicle might end up. We spent a few days looking, eventually kind of gave up. And then 3 weeks later, got a call saying, we found your robot. It washed up on the beach about 100 kilometers north. So very fortunate in that instance to have our vehicle return. I think despite all these challenges, there's been some outstanding successes in the field. Things like the discovery of hydrothermal spreading vents, better understanding of our oceans, new forms of life. All these things have been facilitated using marine robotic platforms. Extremely rewarding, a lot of fun. I think this is a great area to be working in. We have key challenges in those fundamental areas, so in platforms and sensing, navigation and mapping, planning and control, and data analytics. And I think we continue to have a focus on applications and supporting a better understanding of our marine environment. A couple of key future challenges for me are long-range teaming, so getting AUVs and surface vessels to work together, eliminating the very expensive use of manned ships. And we're seeing some fantastic examples of this sort of technology with vehicles able to travel tens and hundreds of thousands of kilometers across our oceans. I think the other interesting work is in underwater intervention, and we're working with a small startup here in Sydney who's developing these sorts of capabilities. And I think getting these platforms to operate autonomously in underwater environments presents some very exciting challenges. So I think our marine program has really demonstrated that we're able to collect rich, high-resolution data sets that are able to complement science, managing the data, transforming it into data products and information to support that science is something that drives a lot of our work. And there are some really exciting future challenges here in the field. I have to acknowledge my support of a variety of different organizations and partners who've been involved in this work, and look forward to the discussion with the panel and the participants online.
That was really great. I want to thank all three panelists. I mean, we could easily have a 3-hour presentation on all your very cool threads of research. I think now we can have an open discussion. I'll pose a few questions from the Slido link that those of you who've gone to the website can see. You can create questions there, which can be posed to the panelists. I think there's a few other questions that some of the panelists or the people have preloaded into the system. Let me mention, because we're already at the 1 hour mark, that the next colloquium is going to be a presentation by Vijay Kumar on July 30th on aerial robotics. I just wanted to get that plug in before we move on to additional topics. So maybe I'll start. I'll start by giving you something that I've been thinking about myself, and then I'll go to Slido and fish out some questions there. And one thing I think that occurs to me is that within this domain of computer science, electrical engineering, mechatronics, robotics is a little bit unusual in the sense that it involves these very, very complicated systems that have to integrate a lot of different pieces together to make them work, which I think actually is a challenge to researchers, right? It's a wonderful thing, but it also makes it harder. I think field robotics takes that and kind of doubles down on it, because not only do you have to integrate systems to make them work in the lab, but you have to make them work in the field, you have to deploy them, all that kind of thing. And so do you have any thoughts on how that changes the nature of research, the nature of graduate school, the nature of funding, how we cope with that as a field? Because it does, I think, make this field unusually tricky.
Maybe I can start, and I could say that, so let me say that robotics is exciting because it's multidisciplinary. To be a good roboticist, you have to be good at everything. You have to be a good mechanical engineer, a good electrical engineer, a good mathematician. You have to understand physics. You have to be a strong programmer. You have to be a good computer scientist. And this is actually a great opportunity because I really feel like at this point in our history, some of the greatest advancements are happening at the intersection between disciplines, which is smack where robotics is right at the center. But of course, that means big challenges because we train students in a much more siloed way. And so I feel like the people who come to robotics are extraordinarily curious, extraordinarily adaptive and versatile, because you have to be that in order to be able to put it together. Also, very ingenious in how you combine things. And I would also say that systems level thinking is tremendously important for robotics. And systems level thinking is a discipline that is still shaping up. And I will tell you that my own aspiration for robotics is to bring much more support for computation and automation, especially at the level of building machines. I sometimes think that our approach to building new robots from scratch by putting by starting with the smallest of components is similar to where programming was before we had compilers, where we had to tinker. I mean, I didn't personally experience it, but I heard about back in the day when programming was all about working with bits and bytes. And I would like to see more computational support for design, fabrication, and programming of machines. So the robot compiler remains a big challenge because if we can provide automation for how we think about some of the lower level systems level aspects of robotics, we can focus on the higher level capabilities.
That's a good point. Roland, I think there's a lot of work at ETH on fabrication related things. Do you have any comment on that?
Yes, of course. I think we're always trying to really integrate this. And I'm extremely happy to see that our mechanical engineering students typically develop really from mechanical to computer science. But I think there is probably coming back on this systems level thinking. If you think about the big challenges of our society for the future with climate change, energy and everything, all these challenges need really system thinking. If you want to really approach these challenges and find solutions, it's not a domain thinking. So we have to train our students much more interdisciplinary. And the second thing, what I claim since 20 years, we should probably think of somewhat a CERN of robotics, or let me quickly explain. So in physics, they know that if you want to do really particle physics experiments, you need big accelerators, and you cannot do this at every university. So you have to do this together, and you need people which are maintaining this, and so that you can really build on top of each other. In robotics, we are still somewhat at a level that everybody starts from scratch. And this we have to find a solution, because otherwise we will never bring all these puzzles together. So once you have solved the localization and mapping, then you need planning and you need probably semantic mapping and so on. But most of our PhD students will start from scratch again. And this, I think we have to find a little bit better solutions. We solve this partially because we have a lot of startups, and then we can build on what the startups made from previous research, but it's still not a perfect solution.
I think the open source community, in terms of software at least, has sort of changed the way, I think a lot of students now will come into the lab and they pick up ROS or whatever, their favorite open source tools, and they can, get access to navigation and mapping and some planning and build on that. And I think that's been a big change from, years ago, when everybody started absolutely from scratch with the algorithmic work as well as the hardware.
Yeah, this helps a lot, but we had actually also a funny experience with this, because then all of a sudden industry thinks, yes, we just download the code from ROS and then we can do localization. And actually they do a first experiment, they're very excited and say, okay. And then they realize this is still far from really industrialized. So we have on some level also go a step further and make this industrialized, so that everybody can really use it and exactly what the system can do and where the limitations are. And
so on that note, do you think our field as an academic discipline, as a research discipline, now has gotten to the point where we've got to have industrial interaction? Again, that's a distinguishing feature, I think, with regard to much of CS and engineering, that the systems have gotten so big and complicated that we can no longer do them only in university, or am I wrong on that?
I would agree, yes. But it's not easy.
I think that it's important to consider that the science and the engineering are important for solving any problem. And so on the science part really belongs straight into the heart of academic activities, research activities. That is important, that is necessary in order to carefully identify the foundations of what might be deployed. When it comes to deploying from university grade to field grade work, a lot of engineering is necessary. And so that requires that we rethink how we assemble the field robotics teams. And academic industry partnerships is one way to do it. Another way to do it is to create engineering teams that can support the work of universities and exist within universities. But there's, and finally, a third way to do it is to really aspire to get to the point where we can make hardware systems and software systems that have a level of robustness that makes them much easier to move into the world. So thinking about robustness as an important challenge in how we design the mechanical body and the brain of the machine is super important.
And I think for me, the IMOS program I alluded to has been very helpful in terms of providing support for the technical support that's required to develop and deploy and maintain these vehicles without while allowing the engineering science to develop through the students You alluded to the importance of, being out in the field and understanding what the real problems are. And I find it very important to take my students, away from the desktop and the MATLAB and stick them on a boat and say, okay, here's some real problems that people are trying to address. And I think it informs the way that they think about their research, and allows us to kind of push the engineering science while also supporting, some real fundamental insights into what's happening around the world.
I think that's great, and it's super healthy. I mean, and by the way, you get to go out into neat places too. So let me take Douglas Bertol from the audience at large asked whether there's a problem with the timelines and expectations temporally of industrial partners vis-a-vis the rate at which academic research progresses. And I think that's a little bit related to this topic that we're talking about now. Any thoughts on that?
I think yes.
So how do you manage that?
Yeah, it's not easy, but typically I tell industry, we will not actually develop something for you. The best we can do some proof of concept for new ideas, but probably the most important thing what we do, we generate the best potential collaborators for the future for you. So if you have a project with the industry, you can tell them, okay, you have at least probably one PhD, 2 PhD on the topic, but then you have probably 20 master students doing something on a topic. And I think this is the most important value industry gets from collaboration with universities. We are actually also, as a researcher, a little bit pushing too much the limit. There is actually also one question about, is Boston Dynamics now solved everything? Is there something left for academia? Boston Dynamics is extremely good in videos, which probably give a little bit of wrong impression what can be done and what not. And they are very secretive what is possible. But it's also research. Sometimes we have this very, very fancy video. YouTube is dangerous, where I think you can easily find videos on robots where you think today it's feasible. We have proven that they can clean up a kitchen. But we are so far from this. And we have to be careful before we publish all this, or we show this video, even if it's written down below the video that this is somewhat teleoperated, whatever. But people get a wrong impression, and then you can only disappoint it. I think we have to be more honest, and then we can have a strong collaboration with the industry.
I'd like to add to that and say that I firmly believe that the role of a university is to advance the knowledge, and we can interpret that at different levels. But the universities have the unique opportunity to think into the future, to think far out, to think 5 years out, 10 years out, and to really imagine and envision. And companies find great value in getting tips from the university about what is coming around the corner. Now, having said that, I would also like to say that as we do foundational work at the university, and we develop robust solutions, not hacked up solutions, it is much easier to take those solutions and turn them into more robust deployable systems. And I just want to point to the 2 robotic systems we developed during the pandemic. So the robotic ventilation system and the UV disinfecting robot are fielded systems. There are hospitals that are using the emergency ventilation system, and there are and the UV disinfecting robot has been operating at the Greater Boston Food Bank for some number of weeks now. Those robots came together very fast, on the order of about a month, from idea to deployed system. And this is because they were grounded into very solid algorithms and very rigorous and robust solutions that were then adopted and extended to the application that they had to address. And so I want to emphasize that while it's important to hurry up and see how our work with long-term time horizon can be used today, having a foundational solution can really help us accelerate the deployment and accelerate the creation of a customized solution for a new application.
Daniela, for the record, could I get you to give a number for how many years of algorithmic research, not just your own, but in the field, led up to the technologies in that COVID, into the UV robot? Because I think I have a guess that it's a big number.
Let me come back to that. I need to reflect, but it's, I mean, I guess it's, I can point to specific work that has been done in my research group, but not just that. It's work that has been done by the community as a whole, and so it adds up.
Stefan, you look
I'd
like
also,
you're going to answer it.
Yeah, I'd also sort of echo Daniela's thinking about, you know, demand really creating a pull for things that have been kind of bubbling along. We've got also colleagues, you know, developing ventilators, and I think there's a real key role there for the enthusiasm of students who, you know, see these problems and can really push things along and get them out. And you know, we're now having ventilators that are being qualified to be used here in Australia. I think there's also two models of translation that tend to work. And one is kind of the interaction with a company that comes and says, hey, we've got a problem and we want to work with you, and, you know, developing big partnerships. And we've had some great success in areas like mining and agriculture and, you know, transportation, logistics. And the other model is more the kind of up and out, is, you know, something's been developed, we kind of identify a key contribution. And I think what we need to do, and some institutions do this better than others, I think, is support that, you know, push the technology out into startups. And I think Roland talked about startups, and I know MIT has quite an enlightened model, I think, for you know, supporting that translation from the lab out into a product. And you know, we've had good success in that as well, and in agricultural robotics and a number of other spin-offs that have come out of the center. And I think we should be encouraging that kind of thing. And we have lots of fantastic students coming through the pipeline who can help with that translation piece.
So a bit related to this is the relationship between classical machine learning, you know, modern machine learning methods, and classical methods that we use in many parts of our field, you know, particle filters and Kalman filters and things like that. Do you think there's a tension between these very new end-to-end kind of methods and some of the classical techniques? And do you think there are problems with expectations regarding the rate of progress as a result? Because, you know, as you know, papers at arXiv are appearing at a rate far, far faster than once an hour now.
I think there is some sort of a tension, because there is a lot of expectation, which and there again there is a lot of results shown which actually look surprising and wonderful, but then if you dig a little bit deeper, it's probably, you have to assume that it's really far from being something useful. And I always think that, for example, machine learning is typically something around reliability or precision of 85%, whatever. A machine, a brake in a car has to work 100% nearly. So there is a lot of this gap. And the interesting part is we are used that computers are not fully reliable. My computer still crashes. Even my smartphone crashes sometimes. This Zoom conference can crash, but a car and an airplane cannot crash. And I think this is because people are coming from a different world. And I think we have to close this gap and see how we can use best of both worlds. I'm also very excited about what you can do with machine learning, but doing it blindly without really trying first to understand what you can do extremely nicely with the more classical approaches is somewhat dangerous and stupid. And I think we really have to bring this together and take the best out of all.
I like the idea of figuring out how to take the best out of both worlds and understanding what the limitations are. And so, I mean, in some sense, the classical techniques have provable guarantees. We can make predictions. We understand how they work, but we are limited in applicability in some sense. The machine learning techniques have a broader scope. They can be applied for more symbolic tasks, more symbolic and abstract questions. And so is it possible to have the best of both worlds, to have symbolic reasoning that when it comes to execution, it's correctly executed? And this is an idea that we are exploring and promoting in my group.
Any thoughts on sim to real? There was a very nice workshop on sim to real that took place at RSS earlier this week, or maybe Sunday or Monday, I can't remember. And I think the feeling was that, you know, closing the gap between reality and simulation through things like domain randomization, sim to real issues, might be a promising saving throw for robotics, so to speak.
Yeah, I mean, I like sim to real. You can crash your robot multiple times in simulation without any consequences.
I can do it in the real world too, unfortunately.
In simulation, you can explore the design space much more extensively, much faster, much more comprehensively. And so, so we've been very interested in sim to real, both for learning control and for co-design of robot body and control system. And we have, it's actually really magical to see that maybe for driving, you can take one data set of a car driving down a road with a particular configuration, and then in simulation you can change the configuration, you can change the trajectory of the vehicle, you can change the weather, you can make it snow or rain, or you can make it sunset, you can change the lighting. There's so much you can do in simulation to help fine-tune your controller. I think that's very valuable. Of course, when you go from sim to real, you still have to make sure that the execution is safe and correct, and you can capture at execution time whatever mistakes or errors were introduced during the symbolic reasoning in simulation.
I have a feeling
it actually comes back to what I mentioned already before. So I think for doing these simulations, you need actually good models. So you have to fuse both elements together in order. And if you have really good models, you can actually really come to reality very fast, I think. And this will get better and better.
Some domains like Stefan's may be quite hard to simulate. I don't know if you...
And I think sometimes those models can also be a little bit brittle if you're not careful. And so having the ability to adapt the models is important in the context of using some of the new learning techniques.
So we got a question a while ago. As we're getting shorter on time, I'd like to pitch it to you. It was about HRI and to what extent is human-robot interaction an obstacle to the domains that you each work in, and to the field robotics domain in general, and to search and rescue in particular?
Well, my opinion is that HRI is extraordinarily important. If we're going to get robots to be used by non-experts, we need to have much improved human-machine interfaces, much more natural, much more intuitive interfaces. I aspire to get to a point in time where we can have the machines adapt to us rather than the other way around, which is what we have today.
Yeah, so it's actually...
Go ahead.
Go ahead, Stefan.
I was going to say one of my first PhD students, he formed a company on the basis of some work he did developing robotics for training special forces. And he said one of his proudest moments was having effectively high school dropouts able to deploy SLAM over very large environments. And you know, the ability to make robust systems that don't need a team of PhDs to deploy them, I think is something that is important, and a lot of that comes down to how people interact with the systems. In our marine context, we have very limited bandwidth in terms of communicating with the robots, and you know, making sure we're getting the right information up to the surface to monitor progress. And we still sometimes look and think, well, what's going on down there? And you know, so that human-robot interaction is very important.
Yeah, I agree. I think it's very important, but it's very task specific. And for a lot of tasks, you don't need so much interaction. You can do it very simple. So today, everybody can fly a drone, taking images from the air. This is somewhat nicely solved. You don't need a training. And sometimes we are pushing also too far because we have to first solve other problems. As long as robots don't understand our world, our intentions, it's very difficult to actually communicate them and that they can learn in our context. So I think we are still pretty far from having a robot to understand how we humans do it. To humans, you just say, go and grab me a beer, and then you start to think about what the whole understanding of the situation is. And once you start to think about the whole decision process a human makes for doing and solving this task, all of a sudden realize a lot of elements robots cannot do by themselves today. So we are not there, and I think there is more fundamental elements still be solved. For example, understanding of the world, understanding of functionality of objects, semantics, before we can really push much further. But of course, controlling a drone doesn't need this, and that's probably very nicely solved today.
And Roland, this takes us back to this point about the need to increase the level of reasoning and the level of understanding of machines, and to really think about how existing modeling techniques fit with machine learning techniques. In other words, how can we combine techniques that enable higher level reasoning with techniques that enable correct, safe execution?
Yeah, but we are even further down. I will say we even don't have a good segmentation at hand. Imagine you have your desk, there is probably 20, 40 different objects. Humans are nearly 100% precise in saying which is an object. You can easily segment this. Computers cannot do it. Of course, we have, again, nice results for some specific trained system, but in a somewhat messy kitchen, then you go from a kitchen from Boston to Switzerland and then to India. I think humans can still do it. Robots or computers are extremely bad in this. So there is a couple of fundamental elements which I think we are missing, and we need new tools. We need additional tools which start differently, and probably, hopefully it will come up at one point.
It's not obvious, though, that we need to solve that problem to achieve many solutions in the robotics domain. You know, segmentation is a great problem, but it may not actually be as critical as we think, especially consistent segmentation.
Yes,
so
I agree.
Let me pitch one last thing to the whole panel, because I think this is kind of the chance for the last question. Do you think, because this is related to the inspiration of biology, right? A lot of robotics and AI research has been driven by a notion of what biological systems do, what we think we do, which is not always reliable. Do you think that biology is the right driving force for our field, or should we ignore it? Or how do you see that? Quickly.
I can probably start. I think we should, in a lot of sense, also think about what we need to fulfill a task easier. You can, of course, bio-inspire. I think you should get inspiration from everywhere, but people actually developed tools, the hammer first, and more and more complex tools. Robots are, in a way, also tools. And I think we should, instead of first asking, should it be inspired by whatever, we should understand what is a task, what actually next generation of tools, complex tools, will ease our life, make our environment more sustainable, for example, in our agriculture. And I think robotics have a lot of potential to work in situations where humans need tools in order to be not exposed to dangerous situation, to unhealthy situation. And there, I think we have probably even a better start to get inspiration from the real field. Back to field robotics.
So I will build on that and say that I see two objectives in our work. One is to create machines that support us with cognitive and physical work, intelligent or maybe autonomous machines that can do more for us. That is one objective. But then there is also the objective to understand autonomy, understand intelligence, and ultimately understand life. And I think that we have a role to play in that extraordinary grand challenge through our work in robotics. Because if we can build machines that work in certain ways, then perhaps we can build, perhaps the natural systems employ similar principles, and we can establish a loop. We can establish a two-way interaction between ideas we get from a biological world and ideas we can input in the biological world. So to me, our work is about the science and engineering of autonomy, about understanding foundationally autonomy and then building devices that deliver autonomy in more capable ways.
Yeah, and I think there is probably a role for the biological inspiration. And the wheel is not something that evolved, but it's a pretty efficient way of getting things around. So, I think there's a role for design. There's a lot of interesting tools in optimization in design, and whether that takes inspiration from biological systems or models and things like that. I think we should be pursuing both. I liked Roland's figure with the 4 quadrants, and I think there's a role for both that user, end use driven research, which can, lead to new developments, but also there's a very important role for pure, basic, curiosity-driven research. And I think as roboticists, we have real opportunities to work along that continuum. There's lots of things that we can take inspiration from, lots of problems that we can look to solve, both sort of real-world things that will drive our research and the things that we just, this is an interesting problem that we should pursue, and I think it's fantastic that we, as a community, do both.
That's a huge set of exciting and invigorating thoughts to close on. I want to thank all of you. This was really tremendously provocative and fun and interesting. I think for the people who are still here, there's still a good chunk of people listening, thank goodness, unsurprisingly, because it's been such a good panel. I think note that you can find more information on the research of each of our panelists, Daniela, Stefan, and Roland, at their respective websites. If you can't remember how to find their websites, you can go to the IFRR webpage and find information there on who they are, their biographies, and their sites. Oh, you can go to my website too. We have some cool field robotics as well. And I want to thank the IFRR for making this possible, and Usama Khatib in particular, who pushed this. And remind you again that on July 30th, the tremendous Vijay Kumar will be speaking on aerial robotics. Thanks, everybody.
Thanks for joining us.
Bye-bye. It was a pleasure to have you here.
Great to see some old friends and new friends on the attendee list. Thanks for coming.
Yeah, and apologies to all the questions we didn't get to. There were some cool questions that we just didn't get to fit in. Thanks for each representing your respective thirds of the earth too, right? Or Roland, all of Europe, Daniela, all of the Americas, and Stefan, all of Australasia. That's good.